Welcome back to our mathematics series. It's been really fun exploring these like fundamental concepts that shape how we understand the world. Today we're gonna take a deep dive into something called a NAND gate. Now, I know it sounds kind of sci-fi, but even if you've never looked into digital electronics before, stick with us. This NAND gate, it actually has some surprising connections to pure logic.
Yeah, and what I find most interesting about the NAND gate is that it's so simple. I mean, it's a logic gate, it's a fundamental building block in circuits, but you can sum up its whole behavior in just one sentence. It only produces a false output if all of its inputs are true.
Okay, so that sounds pretty straightforward, but I'm guessing there's got to be more to it than that, right?
Absolutely. The beauty of the NAND gate is all in its versatility. And to really get that, we need to break down its behavior using something called a truth table. So imagine you have two inputs, we'll call them A and B, and they can each be true, which we represent with a 1, or false, which is a 0. Now, a truth table just systematically lists all the possible combinations of these inputs and the output you get from the NAND gate.
So it's like a map, kind of showing exactly how the NAND gate's going to react to all the different combinations of inputs.
Precisely. And the amazing part is this seemingly simple truth table. It reveals a powerful pattern. So let me show you. If both inputs A and B are false, so 0, the output of the NAND gate is true, so it's a 1. And the same happens if either A or B is false. The output's still true. The only time the output becomes false is when A and B are both true.
Oh, I see. So that's where the name NAND comes from, is basically the opposite or the negation of an AND gate.
You got it. And it's this seemingly simple behavior that makes the NAND gate so incredibly versatile, almost like a universal building block in digital logic.
Okay, so we've got the logic down, but how do engineers actually represent these NAND gates when they're designing circuits? I mean, is it just all ones and zeros on a screen?
Not quite. Engineers use symbols, it's like a visual shorthand, to represent NAND gates in their circuit diagrams. There's a few standard ones like the Melancy, the IEC, and there's even an older one called the DIN symbol. And these symbols let engineers quickly see how the circuit's structured and how it works, even if it's a really complex circuit.
So these symbols are like a language almost for circuit design. Makes it easier for engineers to communicate their ideas and understand each other's work.
Exactly. And these symbols, they're directly tied to the logical expression of the NAND gates. That expression is not A and B. This basically translates the behavior we saw in that truth table into a more formal mathematical language.
Makes sense. So we're connecting the symbols we see to the actual logical expression behind them. And this kind of brings us to a fundamental concept in logic, doesn't it? De Morgan's laws.
Yes, De Morgan's laws give us a powerful way to actually transform these logical expressions. And thinking about the NAND gate, they help us understand its connection to other logic gates. For example, De Morgan's laws show that a NAND gate is logically equivalent to inverters followed by an OR gate.
So the NAND gate, it's more than just a simple idea. It's deeply connected to these fundamental laws of logic that basically shape how we think and reason.
Absolutely. And while I've been talking about the logic behind the NAND gate, it's important to remember that these are all implemented in real physical hardware. So how do we actually go from this abstract logic to tangible electronic parts?
That's a good point. It's easy to get caught up in the theory and forget that there's a real physical thing behind it all.
Right. At the core of the NAND gate, you have transistors and diodes. These are tiny electronic switches that control the flow of current. And by combining these switches in a specific way, we can create the logical behavior that's defined by the NAND gate's truth table. It usually involves a bunch of switches and something called a pull-up resistor, which basically sets those output voltage levels. And there's actually different ways to make these NAND gates using technologies like NMOS and CMOS.
So you're saying these tiny little things, transistors and diodes, are like switches. And by arranging them in clever ways, we can create this fundamental unit of digital logic.
That's exactly it. And this brings us to a truly amazing feature of the NAND gate. It's functional completeness.
Functional completeness. That sounds pretty cool. Tell me more.
It means that you can create any Boolean function, which is the foundation of all digital logic, using only NAND gates. Think of it this way. It's like we found one single Lego block that you could use to build any structure you could possibly imagine.
Hold on. Are you saying that any logical operation, no matter how complicated, can be made just by combining these simple NAND gates in different ways? That's crazy.
It is pretty incredible. And this functional completeness, it's what makes the NAND gate so powerful and efficient when you're designing digital circuits. It's why it's considered such a core element in computer science.
So it's not just a simple logic gate. It's more like a universal key that unlocks the whole world of digital logic. Is the NAND gate the only one that's functionally complete, or are there other gates that can do this too?
There is one other gate that can do this. It's called the NOR gate. But when it comes to CMOS circuits, which are used in almost all modern electronics, NAND gates are usually preferred because they're more efficient.
So choosing between NAND and NOR, it's not just about the logic, but also about like the practical stuff when you're actually building circuits.
Absolutely. You always have to find a balance between the logic and the reality of how you're going to build it.
I really want to see how this functional completeness works, like in real life. Can we see some examples of how other gates are built just using NAND gates?
Sure, let's start with a simple one, like the NOT gate. It just inverts its input, right? Well, believe it or not, you can create a NOT gate simply by connecting both inputs of a NAND gate together.
Wow, so just a single NAND gate can act as a NOT gate. That's so elegant. What about more complicated ones like AND or OR gates?
So for an AND gate, what you do is take the output of a NAND gate and invert it. And for an OR gate, you'd invert each of the inputs of a NAND gate and then feed those into another NAND gate.
Okay, I think I'm starting to see how it works. It's like a logic puzzle, rearranging and combining NAND gates to get whatever function you want. I bet there are diagrams that make this a bit easier to visualize.
Yeah, definitely. Diagrams are really helpful for showing how these combinations work. They clearly show how you can just use a few NAND gates and rearrange them to create a NOT gate, an IND gate, an OR gate, a NOR, XOR, even an XNOR gate. It's like having a toolkit, but only having one tool that can do everything.
That's amazing. These diagrams really help make it clear that the NAND gate is like the ultimate multi-tool of digital logic. But does it stop at just building these basic gates? Can you use this approach to build even more complex stuff?
You can. The functional completeness of the NAND gate isn't limited to just those basic gates. We can actually build things like multiplexers, which are called MUX for short, and demultiplexers called DEMUX, using only NAND gates.
Wow, so we're talking about building the very components that make our computers and smartphones work, all from this one basic element. That's mind-blowing. What exactly do these MUX and DEMUX things do?
Sure, think of an MUX like a train switch operator. It has a bunch of data inputs, and it uses a special selector bit to choose which input to send to the output. A DEMUX works in reverse. It takes a single input and sends it to one of many outputs based on that selector bit.
So they're basically managing the flow of information in a circuit, like traffic directors, and you're saying they can be built entirely out of NAND gates.
You got it. It really shows how NAND gates are the basis for all these complex systems we use in electronics. Starting from just a simple logical operation, the NAND gate, because it can replicate any Boolean function, becomes incredibly powerful and versatile.
It's really a testament to the beauty and the power of simple ideas.
It really is. And it kind of makes you wonder, we've seen how powerful this idea of functional completeness is with circuits, but where else does this ability to build anything to one basic element show up?
That's a great point. I'm really curious about that now. It's like you've planted a seed for a whole new area to explore.
And it's questions like that that keep us curious, right? Always looking for new connections and trying to understand things better. For example, think about set theory in math. You can define every set operation, things like union, intersection, and complement, using just one operation, set difference.
So just like you can make any logic gate with NAND gates, you can create any set operation using only set difference. That's a fascinating parallel.
Exactly. It's a great example of how the principle of functional completeness goes beyond just one specific area. It's about finding that one basic building block that unlocks a whole universe of possibilities.
It makes you wonder if there are other NAND gates hiding out there in other fields, just waiting for us to find them.
That's a great question to think about. It shows how exploring these basic ideas in one area can actually lead to new insights and connections in fields that seem completely separate. It's what makes intellectual exploration so rewarding.
Yeah, it reminds me how interconnected knowledge really is. Sometimes the most amazing discoveries come from seeing the same patterns in different places. And it all started with this idea of the NAND gate. Who knew a single logic gate could lead us down such an interesting path?
It's pretty amazing, isn't it? Sometimes the most simple ideas are the ones that lead to the most profound discoveries. But I want to leave you with a thought-provoking question to consider as we keep exploring. How has this idea of functional completeness, this ability to build anything from just one element, shown up in other parts of math or science?
Now that's a challenge I'm definitely going to think about. It's really cool how what started as a straightforward topic has opened up this whole world of possibilities and connections. And to everyone listening, we encourage you to join us on this journey. Keep asking questions, keep exploring, and who knows what other incredible ideas we'll discover together.
Yeah, it really is fascinating how a concept from digital electronics, can lead to such a wide-ranging exploration.
I'm really hooked on this idea that there might be these hidden NAND gates, like these fundamental building blocks that just unlock so many possibilities. in other fields.
That's the beauty of math and science, the patterns and the principles, they often go beyond just one specific discipline. It's all about recognizing those connections and seeing how they can help us understand different areas of knowledge.
So where else might we find this idea of functional completeness? Like, where is it playing out?
Well, let's look at abstract algebra. It's a branch of math that deals with structures and operations, things like groups. A group is a fundamental algebraic structure. It's basically a set of elements and an operation that combines those elements. And the key here is that you can get any element in the group just by repeatedly combining a single element with itself using that operation.
So it's like having this one element, like a seed, and by using the group operation over and over, you can grow the whole group from it.
Exactly. It's like you have a single key that can unlock every door in a giant mansion. This is really connected to the idea of generators in group theory. A generator is an element that, when you use the operation on it repeatedly, can produce all the other elements in the group.
Okay, I'm starting to see the connection here. It's like with the NAND gate in digital logic, you can build any Boolean function from that one element. And in group theory, you have these generators that can create the entire group structure.
That's it. It's a great example of how functional completeness shows up in different parts of math. And it really highlights how powerful it is to find those basic building blocks that can create a whole universe of possibilities.
It's like finding the source code of a system, like that one essential element that holds the blueprint for everything else. Makes me wonder if there are other areas in math where this concept pops up.
Oh, there are. Let's take a look at linear algebra. It deals with vectors and matrices. In linear algebra, we often work with these things called vector spaces. They're sets of vectors that you can add together and multiply by scalars. Now, in a vector space, there's this idea of a basis. A basis is a set of linearly independent vectors that can span the whole space.
So a basis is like the smallest set of vectors that you can combine to create any other vector in that space.
Exactly. Think of it like primary colors. You can mix them together to make any color you can imagine. In this case, the basis vectors are like those primary colors, and by combining them, you can make any vector in that vector space.
It's amazing how this idea of functional completeness keeps appearing in different parts of math. Every time it shows up, it reveals this deeper layer of structure and how everything is connected.
It really speaks to the elegance and efficiency of math. A lot of times there's underlying simplicity, like a set of basic rules or elements that create this huge and complex world of possibilities. And by understanding these basic building blocks, we can really appreciate how beautiful and powerful math is.
It's like we're learning the secret language of the universe, Like we're figuring out the code that controls how everything around us is structured and how it behaves.
And the journey of discovery, it never really ends. Who knows what other NAND gates are out there waiting for us to find them in parts of math and science that we haven't even explored yet. The important thing is to stay curious, to keep exploring, and to always be looking for those fundamental principles that connect things that seem totally different.
You've definitely given me a lot to think about. I'm starting to see the world in a new way. Like I'm looking for those essential building blocks that can unlock all this complexity. But before we get too lost in the world of math, let's go back to where we started, the NAND gate. We've seen how this seemingly simple logic gate is connected to these deeper mathematical ideas like functional completeness. What are some of the key takeaways you'd like our listeners to remember from this deep dive?
I hope our listeners will really understand how elegant and powerful simple ideas can be. The NAND gate, with its very straightforward behavior, it's a great example of how something complex can actually be built from just a few basic components. And I also hope they'll want to look for these NAND gates in other parts of their lives to find those key elements that open up a whole world of possibilities.
It's a good reminder that sometimes the simplest things are the ones that lead to the most profound insights. Yeah, it really shows the power of abstraction, how just one concept can apply to so many different things.
And that's what's so great about math. It gives us a way to understand the world on a deeper level, a more abstract level. By understanding these big principles like functional completeness, we can start to see connections and patterns that we might have missed otherwise.
It's like we're building up this mental toolkit, and we're adding all these powerful ideas to it, these ideas that help us analyze and understand really complex systems, whether it's a digital circuit or the structure of a mathematical group. It all comes back to these tools.
And the more tools we have, the better equipped we are to take on new challenges and explore new areas, right? So this deep dive into the NAND gate, it's not only helped us understand a key concept in digital electronics, but it's also shown us how important it is in math as a whole.
It's been pretty amazing tracing this idea of functional completeness, from logic gates to set theory, then to group theory, and even linear algebra. And I feel like we've only scratched the surface.
Oh, for sure. I think this principle of functional completeness goes way beyond the examples we talked about today. It's an idea that encourages us to look for simplicity within complexity, to find those fundamental building blocks that lead to a whole universe of possibilities.
And to all our listeners, we really want you to keep exploring this idea too. Look for those NAND gates in your own areas of interest, whether it's music, art, history, or even just everyday life. You might be surprised at the connections you find and the insights you gain along the way.
Yeah, remember, the journey of discovery is often more rewarding than the destination itself. So keep those questions coming, keep exploring, and you'll keep having those aha moments.
That's a great point. So on that note, we're going to wrap up our deep dive into the fascinating world of the NAND gate and all its surprising connections to the broader world of math. Thanks for joining us, and until next time, keep exploring.